see the slides, and you can see it's auto captioning as I actually speak. And it's really interesting because this is using TensorFlow and this is using our technology. And I'm going to go into coding and how to get started with coding this type of technology today. And one of the interesting things about it is, can anybody guess what the second longest word in the English language is? It's anti-disestablishmentarianism. Anti-disestablishmentarianism. There we go. So, and what's really interesting about it is if you look closely at the captions, that it will actually finish saying, or will finish typing out the word before I finish saying it. So if I say it again, anti-disestablishmentarian, you see it actually finished it before I was saying it. So this is what we call prediction. And when it's a really long word such as that one, it's obviously there's only one word that will match as soon as I say anti-disestab, and then it will actually put that word out there, which is kind of fun and kind of cool. And this is the type of thing that developers can start building. And today, like really what I want to do is talk about coding. So I will start by moving to my next slide. And so think about what it is that we do as coders. We generally express rules in code. So for example, if you're building a financial system here where there's a common analytic in stocks called price over earnings or a P over E ratio, and typically you'll write rules for that. Those rules are going to act on the data and give you an answer. The data will be the price, the data will be the earnings, and the rules will be to write a function that divides price into earnings and gives you the P over E ratio. Pretty simple stuff. Or maybe a game, like this kind of brick breaker game or breakout, or it's been called various things. And think about it as a coder. What do you do? Like you have to think about all of the scenarios. What happens when the ball hits the wall? You know, you have to remove a brick. How's the path of the ball going to change? How are you going to update the movement of the ball? All of those kind of things. How's the game going to end? These are all rules that you end up creating yourself. So I always like to say traditional programming looks like this. It's effectively, you create rules, you write rules using a programming language like C or C# or C++, Java, Python, whatever. Those rules are going to act on data and they're going to give you out answers. And it's like all of traditional programming, the highest level summary I could find would look something like this. Now we all get excited about machine learning. And what's machine learning look like on this chart? Well, it's pretty much the same, except I'm swapping answers with rules. So the idea behind machine learning as a programmer, instead of you trying to figure out the rules that are going to act on the data, you're going to get the answers, you're going to have those answers with the data, and the code that you write, the machine learning code, will actually figure out the rules for you that match those answers to that data. Now that might sound a little bit abstract right now, so let me give an example. Activity recognition. Say you're building something for activity recognition, like if you're building a watch or some other device and you wanted to understand when somebody's walking or maybe somebody's doing other activities, like you might have data from that, which is the speed, and you could write a rule that says, well, if the speed is less than a certain amount, we'll say the person's walking. And then you could say, well, I can also extend this rule, and if it's not less than that amount, I can say that they're running. Now, what if I want to do another activity like biking? So then I can say, well, if it's less than 4, they're walking. Otherwise, if it's less than another amount, let's say 12, then they're running. Otherwise, they're biking. So I got some basic rules here that are determining the activities for me. And with the data that I have, I can kind of sort of figure it out. But then what happens if they're playing golf? How do I have any idea that I can detect that activity? I mean, what data could I use based on speed or other things to determine that they're playing golf? So that's why we kind of hit a wall with traditional programming, that we can't always express the rules to determine something. You're going to soon hit the law of diminishing returns if you've got to write thousands and thousands and thousands of lines of code to be able to determine something. And as a result, that's one of the walls that, like I say, I like to describe it as one of the walls that we hit with traditional programming. And you know, we haven't a way of breaking through that scenario. We haven't a way of breaking through those walls to open up new scenarios. So the idea with machine learning is maybe it makes that possible. So if I go back to my activity recognition, now I could gather tons of data, maybe the speed, maybe heart rate, maybe geolocation of the person, whatever data that's possible. And I can get all of this data and I label that data. And I can't figure out what the rules are that determine, you know, here's this bunch of data that a person's walking, here's a bunch that says they're running or they're biking or they're golfing, you know, but a machine might be able to match patterns in that data to the label that I have. So for example here, like I've highlighted these 4 bits, and you know, these 4 bits in this data kind of determine like walking, running, biking, or golfing. It's not going to be that simple, but the idea is that there are patterns in the data that a machine might be able to match to the label to figure out the rules that determine if somebody's walking, running, biking, or golfing in this case. And that leads us to the machine learning paradigm. How do we program this kind of stuff? Well, it's actually quite simple. And generally, if you have a bunch of data and you have a bunch of labels, you're going to start by making a guess. What matches that data to those labels? Then you're going to measure the accuracy of that guess. You know, how good is it based on the data that I know? Then you're going to try to optimize that guess, you know, based on the measurement you made of the accuracy. And then you're going to repeat. And you're going to keep repeating and repeating and repeating. And then over time, your guesses should get more and more accurate. So if I then go back to this diagram and think about it in those terms, it's a case of, and I've just changed the word answers to labels here because that's generally the term that's used. So I have my data, I've labeled the data, and I'm going to try to write some code to do the loop that I spoke about earlier on, making a guess, measuring the guess, optimizing and repeating. And so that's ultimately machine learning. And then once I've done that, I'll have built something called a model. And then in the future, I can pass data into the model, and then that model will give me inferences out. And that's the kind of thing that's happening with the captions at the bottom of the screen now. Lots of answers were given. So for example, mine is actually one of the voices that this was trained on. So it works pretty well with my voice, where it's, there were lots of examples of my voice saying particular words or saying particular syllables, and lots of other voices, not just mine. And then somebody was able to match those to the label of the word that I was actually saying at the time, and we're able to build a model. So now future data coming in, the sound coming from my voice is being passed into that model, and it's making an inference about what word that sound is actually for. But building a voice model is way beyond the scope of a short presentation like this. So I'm going to give a couple of simpler examples. The first one here is that there's a rule that matches the X data here to the Y data. Can you figure out what that rule is? So Y is a function of X. What would that function be? Now, usually people might go, well, I see that the Y is increasing by 2 every time the X is increasing by 1. So it's probably Y equals 2X plus or minus something. And when the X is 0, the Y is minus 1. So it's probably Y equals 2X minus 1. And you'll be right. But think about what you just did. You started making guesses. You started measuring those guesses. You started optimizing those guesses until you came up with an answer. And that's exactly how machine learning works. So let me look at it in code. So here's an example. This is the simplest possible neural network example that I could think of, where you've probably seen neural networks as like a grid of interconnected neurons. And those grid, like there are layers, you'll have layers of neurons, and those layers are all interconnected with each other. Well, this line of code is creating a neural network with one layer, and that one layer has one neuron in it. To be as simple as possible, it's a single neuron neural network. And that's like the keras.layers.dense line that you can see here is defining a layer. There's only one of them, so there's only one layer. And in that, I say units equals 1, so there's only one neuron in that layer. Very simple neural network. Couldn't get any simpler than this. So if we think of our algorithm of making a guess, measuring your accuracy, and optimizing the guess, what will happen is that my initial guess is that that neural network gets randomly initialized. But then when I'm compiling the neural network in my code, I want to measure the accuracy. So I specify that, okay, the loss, measuring the accuracy is also called measuring the loss. And in this case, I'm going to say there's a built-in function in TensorFlow, and there's lots of built-in functions for calculating loss. So I'm just going to say, pick this one, mean squared error. So as you're programming in TensorFlow, you'll see there's lots of different loss functions that you can pick. Often the research will give you indications of which loss function is best for which particular scenario, and that's the type of experimentation that you'll do. But I'm just going to say, measure my accuracy, measure my loss using the mean squared error function. And for optimizing your guess, I'm going to use this thing called SGD. It stands for stochastic gradient descent. And when you see all the math generally in machine learning, this is all encapsulated within the optimizer. I'm not going to go into the math today because I don't need to. I can just pick an optimizer. Then I'm specifying my data. These are the X's and the Y's that you saw earlier on. And then the process is called model.fit, where I'm basically fitting the X's to the Y's. And you see here a line that says epochs equals 500. That just means it's repeating this loop 500 times. The first time the neural network is randomly initialized, and a unit in a neural network, just as a handy shortcut, basically learns a weight and a bias. So where I said Y equals 2X minus 1, the 2 is the weight and the minus 1 is the bias. So I can do a scenario like this with a single unit. And when I have a single unit, that weight and that bias are randomly initialized. That's my guess. So 500 times when I say model.fit, it's going to make a guess. It'll measure the accuracy of it. It'll optimize it, and it will repeat all of this. So after 500 times, it will then try to, it will have a model that will have tried to match these two to each other. And then you can do a model.predict on a new piece of data that it hasn't previously seen to get the answer for that. And here, if it's learned y equals 2x minus 1, and I pass in 10, what do you think the answer would be? Well, most people might think it's going to be 19, and you think you would be wrong. You'd be very close to being right, but you'd be wrong, because remember that this is giving me a high accuracy and there's a high likelihood that the answer will be 19. But given that my data is only 6 items of data, there's a linear relationship between those 6 items of data as it is now. But if there was a lot more data, for all we knew, it could skew in either direction. And that kind of probability is built into the neural network. But if you were to run this code now, you'd probably get an answer that looks like 18.989 or something along those lines. So it would be very close. It would be a prediction. And it's tried to figure out the rule that maps these to each other, and it would give us something pretty close. So let's take this to a little bit more sophisticated a scenario now. The same pattern that we just saw for that very simple example can be used for more sophisticated things like computer vision. So for example, if you look at a picture of something and you know what that picture is, in your brain you're going to say this is a picture of whatever. But a computer doesn't know what it is, and it's kind of like if I show you this picture now, and you've no idea what's in there, and it just looks like a big blur. So how would you start to parse what's in that picture? So as you look at parts of the picture and you can see what's in them and you understand what they are as a human, then you might start putting these things together. Your brain will start putting these things together and show you, and like you'll understand what's in the image. So for example, if I say, okay, well in this part of the image I see these things. Now you and I know that these look like legs, and they look like human legs. And if we have lots of images that all have these kind of things in them, and we know that all of these images are images of humans, then when we start seeing a feature like this one, we'll start to associate that with humans. Similarly with these things, and again, you and I know that they're hands. A computer may not know that they're hands, but if a computer sees a lot of these things in an image, and all of those images are labeled as human, and it starts to associate, well, when I see these things and it's a human, and I see these things and it's a human, and then I start seeing this thing and I'm already told that it's a human, then the computer can start putting these together and say, okay, well, when I see these 3 features, and I'm told that these 3 features are all in images that make up a human, now I can start understanding what a human is, or at least from a pictorial perspective, what a human is. And when I see future pictures that have these things in them, then I would say, that is actually a human. This is what a human looks like. And here's how we can start teaching a computer to recognize what a human looks like. And similarly, if I start seeing features like these 3, and I'm given thousands of images with these things that I see in them, and if all 3 of these things are present, for example, then and all of those images, I'm already told that they're a horse, that it's labeled. In the future, when I start seeing these things in an image, I'll start to recognize that that image is actually a horse. Now, the idea is then with image, and if you've done any kind of image processing, you can create filters that you run over an image. For example, if you've used Photoshop, you might have filters for sharpening images, for enhancing edges, or for bokeh effects and that kind of thing. And those are just filters. They're mathematical transforms that operate on an image. And a computer is very good at having mathematical transforms. So if you could figure out the filters that will extract features, and if those features are always present in an image that's labeled in a particular way, now, by learning what those filters are, you can start applying those filters to images, and you can start understanding what's in those images. Now, I've used legs and hands and face here as an example because those are things that we as humans can relate to as features. But when a computer starts applying filters to these kinds, it might see things that we don't recognize and we don't identify at all, but it will always see these things as present in an image. And if that image is labeled and those things are consistently in the same labeled images, then it would use those features to identify the image. And if you've seen things like Deep Dream, where it's like these sometimes very kind of trippy images, what's actually happened there is like when a computer has been trained to recognize particular images, the filters that the computer uses to recognize it are applied to the image, and then a human sees that image and it might look trippy to us. And like I say, filters can extract features, hands or ears or things that we wouldn't understand, but the computer could see consistently with within images of the same label. So then those filters can be combined with labels, like I said, to make a prediction of the image contents. and the filters that will match a particular label can be learned over time. So now, if I have an image and I pass the image into a model, so the image is just the data, the model has learned a bunch of filters, it applies those filters over the image, and it sees something like this, it will go, I recognize that's a human, and off we go. So if I go back to the machine learning paradigm that I was showing earlier on, it's the same loop. You're going to make a guess, you're going to measure your accuracy, and then you're going to optimize your guess and repeat. In this case, the guess will be, I'm just going to randomly initialize all these filters. I'm going to apply them to the images, and then I'm going to make a guess which ones match labels to images. So for example, if I had horses and humans that I was showing earlier on, now the next step would be, okay, I've come up with a bunch of filters in my first step. I've applied those filters to the images, and I kind of sort of think these filters determine a human, these filters determine a horse. Let me measure that. It probably doesn't do very well. If it's random the first time and there's only two classes, like a horse or a human, it's a 50-50 chance. So your accuracy is probably like 50-50. If you're a little bit over 50%, you're heading in the right direction. But then you can use the data from the previous steps to tweak your set of filters and to constantly repeat the loop and go on and on and on repeating it. So again, if we're seeing something like this and we say, okay, when we see these, when the filters that we have learned are applied to this image and it gives us features that are always a human, now we know that we're looking at an image of a human. So what would this look like in code? Well, the idea is it'll look a little bit like this. So it's a very similar thing to what we saw earlier on, where I'm defining a sequence, and I'm defining a sequence of layers. Earlier, I had a very simple one where there was only one layer. Now, a lot of this code, if you're not familiar with it, might look a little bit weird to you. So these things, the conv2D, it actually stands for two-dimensional convolution, and that's just another word for a filter. So what I'm saying in this case is, like, I'm going to create 16 3x3 filters on my image, and then I'm going to have another layer of 32 3x3 filters, and then another layer of 64 3x3 filters. So if you can imagine, my image will have 16 filters applied to it, giving me 16 new images. Each of those 16 images will have 32 filters applied to it, giving me 16 times 32 filters. The results of each of them will have 64 filters applied to that, so there's a lot of filters going on here. So ultimately, I'll have 16 by 32 by 64 filters. So all of my images are getting, filtered and creating tons and tons and tons of new images. So one little trick that you can do is this thing called a max pooling, which is a way of compressing the image while enhancing the features. And I don't have slides to show it now, but if you take a look at some of the other material that's out there, the idea is that what's kind of cool about this with the max pooling, if I say max pooling 2x2, what it's doing is it's taking squares of 4 pixels in every image and just picking the biggest value of each of these. So the image will end up being a quarter of the original size, but the actual features within that image that got filtered out by the filters in the previous layer will be enhanced even though we're losing information. So this is a way of reducing the size of the images so we can be memory safe and as we continue to train, while we're having 16 times 32 times 64 filters being learned. Then at the end of it, the dense here is a neural network. This is your traditional neural network we see where you have neurons that learn features, that learn weights and biases. So the idea is that all of those features that have been extracted by all of the filters above, they are then being classified, using a dense layer to the final classification where there's only one neuron in it. And generally, if that neuron value is close to 0, it's going to indicate a horse. If that neuron value is close to 1, it's going to indicate a human. And the reason for that is it's actually alphabetical order based on the label. HO comes before HU in the alphabet. So back to the similar code to what we saw earlier on, I have an optimizer and I have a loss function. So again, my accuracy is measured by the loss function. In this case, I'm picking something called binary cross entropy as my loss function. The binary is kind of a clue there that I'm detecting 2 different classes, a horse or a human. So binary, there's one or the other, 0 or 1. It's going to push it towards 0 for a horse. I'm going to push it towards 1 for a human. My optimizer in this case is called RMS prop, root mean square propagation. And then the idea is there's parameters in that. In this case, I have a parameter called the learning rate. And the learning rate is the rate at it's a factor that you multiply on top of the optimization to determine the next guess. So you want to pick a learning rate in this case, which if it's too big, the optimization is going to go crazy. If it's too small, it won't learn anything. So there's a little bit of tweaking that you do here. And in this case, for this demo that I'm going to show, I use a learning rate like this one. And then all you're going to do is fit. So I have a model that I'll show it in a moment. I have my training data that I put into it, and the fit here, the 12 epochs, I'm just going to go through this loop 12 times. Actually, in the demo, I think I did it 15 times, but the idea, again, is it's going to make a guess, it's going to measure the accuracy of the guess, it's going to optimize that guess, and it's going to continually repeat. So if I switch to a demo for a moment. There isn't time to train it now. I trained this one a little bit earlier, but I just want to show while it's training. So if you remember earlier on, I was saying I had my horses and my humans. In this case, I have 1,027 images of horses and humans that have been split into two classes. I think there's 527 humans and there's 500 horses. So it's not a lot of data. I only trained it for 15 epochs. We can see here every epoch took about 45 seconds. So this was only about 10 minutes worth of training to get this. So as you imagine, it's not going to be a very accurate model. Often you're going to have much more complex models than this that train for much longer to be able to get a highly accurate result. But if we look here, like my first time through, the first guess that it made as to all of these filters and tried to figure out which filters were for humans and which were for horses, it actually got it right 57% of the time. So remember I was saying 50% would be a coin flip because there's only two classes. So my initial guess was pretty good. I then optimized and guessed again. It went up to 68%. I optimized and guessed again. It went up to 69%. And then after 15 iterations, it was getting up to like 82, 83%. It ended up on 76%, so right about 3/4 of the time. And if I run the model and try to show you an example with some images that I preloaded, so I'm going to run this. I'm going to choose some files from my system. The names of the files should give it away. And so you can see what's in the image. The one that's suitcase is a woman carrying a suitcase. So if I upload them here, we can see that the horse 085.png, it detected as a horse. The human is a human. The one that was a suitcase, a woman carrying a suitcase is a human. And this woman, of course, here again is also a human. So it got it right 4 out of 4 here with these images. It's not always going to do that because the accuracy here was like about 75%. So it should get it right 3/4 of the time. I also had a validation set, which is while I was training, I was also testing the network with images that the network hadn't previously seen. And the idea behind that is to try and avoid something called overfitting, whereas if you train it and it's brilliant at recognizing what it was trained on, and it may not recognize other things that it hasn't previously seen, that concept is called overfitting. The way I always like to say it is like, you know, if an alien walked into the room and the alien had never seen shoes before, and you show it 1,000 pairs of high-heeled shoes and you say, these are shoes, then that alien would only recognize high-heeled shoes as shoes, and then you show it a slipper or a sneaker, it wouldn't recognize that as a shoe. That's the idea behind overfitting. So part of the process here as I'm training is I also want to make sure that my network isn't doing really, really well at the data that it has seen and it's been trained on, and doing really badly on others. And as you can see here, I'm not overfitting in this case, so it's a pretty good network where it's about 76.73% right on data it hasn't seen before and 76.64% right on data that it has seen before. So it's not a great one yet, very low accuracy, it's only about 75%, but this was one that was just trained for about 10 minutes. So I think I'm at my time there, and if anybody has any questions, I guess I can take them now.
Awesome, great. Thanks for the great introductions. I just see a comment from the chat says this is one of the best introduction to TensorFlow ever.
Oh, thank you. Thank you very much.
Okay, great. So let's go over the Q&As, and I see we have quite a lot of questions. Are you able to click the Q&A tab?
Yeah.
And
it's on a different screen, so I'll be looking away. Shall I just go through them myself?
Yes, you can just go through them from the top to the bottom.
Sure. So I'll start with, let me go to the top. So Ruchita asked about TFX. That was from the previous, but yes, TFX is free and open source. Where should I? Okay. Suyash asked about the auto captioning. Is it on browser or native app? It's in the browser. So I'm just showing Google Docs in my browser. And if I can come back here and resize it, we'll see we're just in Chrome. And I'm just showing it in there. And when I present the auto captioning, I just turn on the captions button. You need a decent Wi-Fi connection for it to work. And because it's passing my voice stream up, it's getting it classified, etc. But yeah, that's in the browser. Surendra Kumar asked, can we get access to free ML AI training with lab exercises? So the answer to that is yes, absolutely. There's a few places where you can get it. I teach on Coursera, and Coursera courses can be audited, so you don't get the certificate at the end of it, but you do get all of the training material. Optionally, you can also, if you go to YouTube and you search for something called ML Foundations, on there, it's a 10-video course that I taught that teaches basic ML and then teaches computer vision, a little bit like what I showed here, as well as natural language processing. And that has a bunch of hands-on labs that you could do. All right, let's see what's next. I keep scrolling, sorry. Is there a notebook replicated in what's being demoed here? Yes. My recommendation would be to go to YouTube and go to the ML Foundations course that I mentioned earlier on. And there are links in that to all of the hands-on labs and notebooks to do things like I showed here. And Horses versus Humans is one of them in there. David asked, how do you come up with epoch values or filter values? It's a lot of trial and error. Often it's, like just say, it's a lot of trial and error, seeing which ones actually work. There is a thing that you can get called Keras Tuner. And the idea with Keras Tuner is that you can ask it to tweak different parameters and look for specific results. So for example, I could say, tweak my filter values, tweak my learning rate, tweak my number of epochs, and keep training until you get 95% accuracy. And then it will go through and train them and then find out the ones for me. So it does a lot of that brute force work for me. If you like to read a lot of academic papers, that kind of thing, there's often advice in them for specific scenarios about filters that you can use, neural architectures that you can use, those kind of things that you can use. But I generally find that for a specific scenario like this, often just a lot of trial and error is the best way to learn. Okay, let's see. So next one is David asked, filter deployed 16, 32, 64, why not these other things? It's the same thing, it was just trial and error. Just remember, the more filters that you're using and the more layers that you're using, that means more processing that you have to do, and your training is a little bit slower. So the results that I have here, a lot of that was from me just doing a lot of trial and error. Okay, is there any package in TensorFlow to support reinforcement learning algorithms, from Sam KH? The answer to that is yes, there is. There's a thing called TF agents to do that. My recommendation would be to go onto YouTube, go to the youtube.com/TensorFlow channel, and at the ML Dev Summit that we had back in March, there were a couple of presentations around TF agents, and that would be the place to go to learn about it. Okay, so Jish AISys asks, these are great surnames, AISys, so these aren't surnames, sorry. I thought lots of people had the name AISys, sorry about that. So what are the current projects that Google is working on using TF? Internal projects, we've so many. I can't really list them all out here, but we're using TensorFlow extensively in almost everything that we do, because ML, I think, really is because of how I showed here, how ML opens up new scenarios that weren't previously possible, then things like auto-captioning on slides like this, we're using TF to open up. Think about how we do things, be it YouTube recommendation, be it Android, be it the search engine. We're applying machine learning to all of those. My favorite machine learning story, actually, I learned when I first joined Google, and that is, you probably know Google are quite famous for having cafes, at least when offices are open pre-COVID, cafes that serve food and free food. But the problem is, when food is free, food can be wasted. So one of the first applications for machine learning inside of Google was actually how much food should we cook? And so as a result, to minimize the amount of food that's being wasted. And as a result, through using this, the food wastage that we had when cafes were open was absolutely teeny tiny. So even little things like that, machine learning can be used for, I think is really cool. Is the code for auto-captioning available somewhere we can play with? The answer is yes. There is a Google Cloud service that you can take a look at. I'm not sure exactly what the URL is, but the cloud service for taking a stream of audio data and turning it into captions, that's used here. Sorry, the technology that's used here has been turned into a cloud service, so it's up to you. You can give it a shot. Rahul asked, ReLU versus Sigmoid, which do you prefer? So it depends. So in middle layers of a neural network, if I've got a lot of dense layers, definitely ReLU. And so I would say in those cases, definitely ReLU. And the idea behind ReLU, for people who, if you're not familiar with these kind of things, is that every layer in a neural network can have an activation function applied to it. The ReLU activation function basically is as simple as saying, if the value coming out of the neuron is less than 0, make it 0. Otherwise, keep it as it is. And the reason for that is, like, say I have two neurons coming out of a network. I'll go this way. Say I have two neurons coming out of a network, and this one is outputting -1, and this one is outputting +1. They'll cancel each other out. And you may not want that to happen. So if you have a ReLU function on these, this -1 would become 0, this 1 would stay as 1, and they wouldn't cancel each other out. So to answer that question, ReLU for those internal layers, so you don't get that cancellation. Sigmoid is usually on your final layer, where the idea is, like, if you've got a final layer, like in this case with a single neuron on it, the idea about sigmoid is it kind of pulls the values apart. So like the horse in this case would be more likely to go towards 0, and the human would be more likely to go to 1. So like I said, it really, really depends. Ricardo asks, is there any technique that can reduce the amount of training required to classify an image? I know a service for labeled image classification with 95+ accuracy with only 100 images. One technique, and I used it in this demo, although I didn't have time to show it, is called image augmentation. And the idea behind image augmentation was, if you can imagine the idea of, I was talking about overfitting earlier on, and if you want to train an image for, train a network example for determining the difference between a cat and a dog, right? Cats have pointy ears on top of their head, like little triangular ears on their head. And if you don't have many images, they probably all have the ears upright. The idea behind image augmentation is that as you're training, you're also amending the images, like rotating, so that the ears can be in different aspects, or maybe color modification. If you only have cats with green eyes, color modification on the image could give it blue eyes or red eyes or whatever, those kind of things. So using image augmentation, you can artificially enhance the size of your data set so that you could see scenarios that you hadn't previously seen. One example that I'd like to share is in the horses versus humans that I just gave. All of the images that I trained it on were of full body humans. I'll give an example of one here. Actually, I have one on my desktop. So this is one of the, I use synthetic images, so this is one of them. So you can see it's a full body human. We see her head, arms, legs, feet, all of those kind of things. But often when you want to recognize an image of a person, for example, you might see something like this, where in this case, this woman kind of looks similar, same kind of body shape, same hair, but we don't see her legs. So when we're training with a data set like this one, we're basically telling it this is what a human looks like. A human has legs. You and I know that this is a human, but we don't see any legs. So one of the augmentations on this could be zooming into the image. So as we train, we could be training it on something that looks, I don't know how to zoom with this, but maybe something that looks a little bit more like this, where it's like, hey, this is still a human when she looks like this. And as a result, be able to recognize images like that as well. So that's like, just one way if you don't have a lot of data, to be able to artificially stretch your data so that you can train on smaller data sets. I know we're running short on time. Do I have time to take any more?
Yes, I think we can take a couple more.
Okay, so let me see. Are there any projects?
To the bottom, they are quite.
Okay, let's see. What can we do for image class imbalance? I think the same thing that I just mentioned, image augmentation could be used there. Like if I only had 100 horses and 10,000 humans, I could use image augmentation to create more horses. Do you model any of your AI work with differential equations? Absolutely, yes. So all of these are using differential equations under the hood in the optimizers. In some of the tutorials that I'm working on, there's a new course coming out from Coursera. I will actually teach how to do that using the differential equations, using something called gradient tape. But I found that to be successful immediately with machine learning, you really don't need to get into that stuff because you can use like off-the-shelf optimizers instead of doing your own. I'm working on a personal project for auto-tuning Keras. Can I extend this with the Google community? Who would I reach out for this? I think I would post something on, there's a site, discuss@tensorflow.org, where you can share with the TensorFlow team and the community. I would say that would be the place to do it. That was from Jish. And let me do one more. Let's see. Can I provide links to the free training that I mentioned? Sure. It's easy to find. Just go to youtube.com/TensorFlow. And you'll see a playlist on there for ML Foundations. That would be a good one to do. Otherwise, go to Coursera and look for TensorFlow in practice. That would be a good one to do. And I'm sure we can share all the links on the Slack.
Awesome.
That puts us at